It's a great pleasure to have Shreya Vardhan from MIT, and she's going to tell us about bound entanglement in thermalized states and black hole radiation. Take it away, Shreya.
Great. Yeah, thanks a lot for the invitation to speak at TFR. So today I'm going to be talking about this recent paper with Jonah Kadaflam, Hassan Shapurian, and Hong Liu. Okay. So the plan for the talk is to start with some background and setup about mostly about mixed state entanglement. And then we'll discuss something called an entanglement phase diagram. First in the case of random pure states, which we'll treat as a sort of reference case for this talk. And then we'll discuss the finite temperature phase diagram, which is the main result that I want to tell you about, and the implications for black holes. And then hopefully there will be time at the end to go into more detail about the methods that we use. Great. So yeah, to start with, just some background and setup. So the question that we ask is in the context of the universal process of thermalization. So quite generally, we expect that if we have a chaotic quantum many-body system or even classical many-body system, then if it starts from some out of equilibrium state, it should eventually reach some kind of macroscopic equilibrium at late times. Okay. So in the quantum mechanical case, consider some mixed state rho, which is obtained from the time evolution of a chaotic quantum many-body system at late times. For example, this could be obtained by starting with some initial mixed state rho 0 and evolving it unitarily, or it could be obtained by starting with some initial pure state and then evolving it with some unitary time evolution, and then tracing out some subsystem to get a mixed state. So in both of these cases, at late times, this state should macroscopically resemble some equilibrium density matrix, which we'll call rho equilibrium. So for example, this could be the canonical ensemble or the microcanonical ensemble. And what I mean by this macroscopic resemblance is that if you look at expectation values of some few body observables in these two states, then they're quite close to each other. Okay, but this doesn't necessarily mean, and in fact, in general, this actual state rho will not be close to the equilibrium density matrix by measures like trace distance. Okay.
Sorry to interrupt, but maybe this is the next slide, but do define trace distance for us, if you don't mind. Just one.
Oh, yeah, so that is just defined. So I haven't explicitly defined it in the next slide. But if you were to just take the difference of rho and rho equilibrium as matrices, and then look at its eigenvalues and sum up the absolute values of the eigenvalues, that gives you some measure of the distance between two states. And for instance, if you know that two states are close in trace distance, then you know that if you make any measurement, they're going to be quite, in the two states, any measurement will be extremely close.
Right. Okay, so it's some of the sorry, just to say, actually, some of the absolute value of the difference in the eigenvalues of rho and rho equilibrium. Huh? Is that right?
That's right. Yeah.
Sure.
Yeah, that's right.
Okay, so
maybe
rho
with
and
a
rho
factor of
equilibrium may
1/2.
not be simultaneous. Okay, so they may not be simultaneously diagonalizable, but nevertheless, you take the eigenvalues of rho equilibrium. Perhaps you order them in some way when you compare, or what do you do?
No, sorry. So you
just
take
to understand one. Sorry.
Yeah. So you take the.
You take rho minus rho equilibrium and then diagonalize it, I guess.
Yes, exactly.
Huh?
Yeah.
Okay, got it. Sorry. Excuse me. Yes. Sorry, Shiraz, please go ahead.
Another. Shreya, suppose your subsystem was a small part of a bigger system, and then you traced out the rest of that bigger system. Then would something even stronger be true? Would it be true that rho there goes towards some canonical density matrix more than for special observables, but just becomes the thermal sort of density matrix for that small subsystem for all observables?
Yeah, that's right. So if you take the system B to be some, say if you have some full system AB, and then if A is smaller than B, then in general you expect that this rho will actually be much closer to rho equilibrium. But in general, if you trace out some B which is smaller than half of the full system, then these two states will be far in trace distance, but they could still be close in expectation values of few body observables.
Excellent. Then in the limit that the system that you keep is the size of the system that you keep divided by the size that you're tracing out goes to 0, so that the system that you keep is a small part of the full system, then it would become exactly the thermal density matrix.
Yeah, that's right. That's what we would expect.
Thank you.
Yeah.
And just one quick question. When you say rho equilibrium, do you mean that with respect to some approximately local Hamiltonian? Is this right? Or
so it doesn't have to, so this should be fairly general. So yeah, you could, for example, take it to be a local Hamiltonian, or you could have non-local interactions, and in both cases at sufficiently late times you should see equilibration.
But couldn't I write any density matrix as the exponential of some Hamiltonian? And so, I mean, I'm just trying to understand, like, what is the criterion for it to mean something like an equilibrium density matrix?
Right. So I mean for instance, if you take e to the minus beta h, then it would be the Hamiltonian that corresponds to the time evolution that goes.
Oh, I see. That particular Hamiltonian. Okay, I see. Got it.
Yeah.
Thank you.
Yeah. So for that system, so the equilibrium density operator for whatever system you're looking at. Okay.
Shreya, if I might ask a question. So this trace distance that you defined, so I know another definition, which is that if you take the square normalized rho and you want to know how far rho is from rho equilibrium, then you square normalize rho. That is to say, you define rho divided by square root of trace rho square, so that it is square normalized. And then you square normalize similarly rho equilibrium. And when you take a trace of this, like a scalar product of two square normalized density matrices, namely trace of square normalized rho times square normalized rho equilibrium, and how close this is to 1. So this is one example in which this is one definition, which actually works out in the example that Shiraz was talking about, namely that you take a small subsystem, which is much smaller than the total sample size. And then indeed, it becomes like the rho equilibrium of that subsystem, but in that definition. So I'm not sure whether my definition is the same as your definition.
Yeah, so I think what you're describing sounds similar to something called the fidelity. Right? It's so I think all of these different distance measures are pretty closely related to each other. So I'm not sure so I think definitely in the case of pure states, I think what you're describing is the fidelity. And
fidelity I thought involved overlap of wave functions.
Right, and then right. So there's some generalization of fidelity to density matrices.
I was just worried about this issue of comparing eigenvalues, because Sandeep raised this point about which way you tag the eigenvalues. I mean, how to order the eigenvalues and so on.
So you don't have to order them. So you can just subtract. You can just write down the difference of the two matrices and then diagonalize that, and then sum the eigenvalues of that difference.
I see. Yeah, maybe these are the same things. Okay, all right.
So definitely with the fidelity and the trace distance, you have inequalities between them in both directions. So essentially, if one is small, then you know that the other is small as well.
Nice.
And then I think that that's probably also true for other measures of distance. So I'm not sure that I've seen exactly the one that you're talking about before, but usually they have pretty similar behaviors.
Okay, thank you.
I'll just say one thing. You must, of course, go on, Shreya. But Gautam, I was also thinking about exactly your measure. And there is some discussion which is actually related to our upcoming journal club on Preskill-Hayden. so the measure Shreya is using is sometimes called the trace one measure, right? Because you just look at the eigenvalues, and yours is related to the trace two, the rho square. And there's a Cauchy-Schwarz type of inequality that bounds, the difference as computed by your measure, Gautam, in terms of Shreya's measure. But anyway, let's discuss it. And so as Shreya was saying, if let's say the trace one, my limited understanding is if the trace one measure is small, that will bound the trace two rho square type of measure as well. Okay, but anyway, yeah, it's a good question. Let's discuss it sometime. All right, sorry. Please, sorry, Shreya.
Yeah, no, that's good. Okay, great. So yeah, so essentially this is the type of state that we're interested in. And the question that we want to ask about it is that if we just divide our full system A on which the state lives into two parts, A1 and A2, then how much entanglement is there between A1 and A2? And this is a question which has been asked, similar questions have been asked many times in the literature. So for example, Page asked a similar question about pure states. And in that case, he just used the entanglement entropy, which is sufficient for describing entanglement in pure states. So it's just defined by taking the reduced density matrix of this state rho in the subsystem A1 by tracing out A2, and then just looking at minus trace of rho A1 log rho A1. Okay. So essentially the approach that Page took was to look at this quantity in random pure states in any system A, and then make a prediction based on this result for any quantum chaotic system for black holes, because we know that black holes are expected to be chaotic systems. So in this talk, we'll be taking a similar approach to Page, where we'll be asking this question about general chaotic quantum many-body systems, but we'll be especially interested in applications to black holes. Okay. And we'll be asking the question about mixed states rather than pure states. So let me remind you why we should think of black holes as an example of this. So we can imagine that we start with some isolated star, which is in some pure state psi 0, and then it undergoes gravitational collapse and forms a black hole. And eventually that black hole, we know, emits thermal radiation, and it shows other properties which are similar to thermalized states. For example, if you look at correlation functions of observables in this black hole state, then those have a very similar behavior to correlation functions in thermal states. Okay, so so our question in this context will be about considering the radiation of the black hole and dividing it into two parts, R1 and R2, and then asking about correlations that are present between R1 and R2, and in particular entanglement correlations between R1 and R2. Okay. And of course, this is a mixed state because the state on the full system is a pure state, but we don't have access to the black hole. So we'll just be looking at the radiation. Okay. Any questions about this? Okay. Great. So why is it that the entanglement entropy is not sufficient for understanding the mixed state case? So let me remind you. So the most natural measure for studying correlations between A1 and A2 is just the mutual information, which is defined in terms of the entanglement entropy that I defined on the previous slide. So this is just defined by adding the entanglement entropies in A1 and A2, and then subtracting the entanglement entropy of the full state. So we know that in the case where we just have a pure state, if it's unentangled, then it has to be a product state. Okay, so it has to have this kind of tensor product form, and its mutual information is necessarily 0. So for pure states, the mutual information being non-zero is exactly equivalent to the state being entangled. But this is no longer true when we go to the case of mixed states, because if you consider an unentangled mixed state, then in general, that's a separable state. So it has this kind of form, where it can be some convex superposition of product states. Okay, so a state like this, if the number of terms in this sum Q is bigger than 1, then you will see that the mutual information is non-zero. but this is not an entangled state. So there are some ways of seeing that it's not entangled. For example, it's still somehow all the correlations in it can be given some kind of hidden variable description. Okay. So somehow this is telling us that in mixed states, the mutual information reflects both classical and quantum correlations. Okay, so it's not just telling us about quantum entanglement. So this is the motivation for introducing a new criterion. And for mixed states, so if you wanted to find some quantity which would tell you for an arbitrary mixed state whether it's separable or entangled, then somehow doing that is an NP-hard problem. So you can actually not find any easily calculable criterion which does that. So you have to define a new criterion, which is called...
Sorry, Shreya, could you please go back to the previous slide?
Yeah.
Yeah, so can you go over the definition of the unentangled mixed state, or when it is separable? I didn't quite understand the definition of separability.
Yeah, so the definition is just that you can write it as some convex combination like this of product states. So all of these PI are like kind of like classical probabilities. So they're between 0 and 1 and they add up to 1. Yeah, so I don't...
I mean, you are not demanding that it should be a product of row A1 and row A2. You are still allowing linear superpositions of this stuff, right? I mean, what I mean to say is that for a pure state, if I allowed linear superpositions like this, then that would have been entangled, right? I mean, if upstairs you have this equation psi equal to phi1 times phi2. Instead of that, if you allowed a linear superposition of phi1i, phi2i, and then attach some coefficients and add to them, that would be a pure state, but it will be a non-factorizable state. And now you are writing something which seems like not separable quite, but you're
right.
Yeah,
right. So if you took a pure state like that, which was actually entangled, so it involved some linear superposition, and you wrote down the density matrix for that state, then you wouldn't be able to write it in this form. So the density matrix for that...
because of the absence of some cross terms, is that the thing here? I mean, it's still
exactly.
walk diagonal.
Somehow you should think of this as some kind of like incoherent classical superposition. So it doesn't have.
So let's contrast with what would not be. So an entangled mixed state would be what then? I see. It just cannot be written in this form. That's all.
Exactly. That's just the
it would involve the factors inside the row A1 and row A2. I see. Maybe that's the thing.
Sorry, Shreya. I mean, are there any constraints on the coefficients PI? If not, I would imagine any matrix would be written like this.
The PI are all real numbers which are between 0 and 1 and they add up to 1.
Which are between 0 and 1. I see. So entangled would be when PIs don't satisfy this problem.
Yeah, that's right. You can see it that way. Yes.
Thanks.
Yeah. So there is an old paper by Werner which I haven't read, so I wouldn't be able to tell you the exact argument, but essentially, I think it's been established that states like these. For instance, they satisfy generalized Bell's inequalities. So somehow you can think of them as having correlations, but not anything that requires quantum mechanics to explain the correlations.
Okay, it's not very clear to me, but I'll try.
Yeah, it's not obvious. Yeah.
Okay. Right. Yeah.
But for our purposes, so sorry.
I mean, it's intuitively. No, I'm just saying that's intuitively very plausible because the two paths are not correlated with each other except for a probability that each one has, so it's some hidden variable. Anyway, yeah. Okay. It's not an intrinsically quantum thing. Yeah. All right.
But you're still allowing linear superpositions. I mean, hundreds of linear superpositions.
It's true. So there's a classical Shannon entropy here, pi log pi. But you can replace that with some hidden variable. There's no analog of the quantum entanglement per se in this.
Right. Yeah. Actually, yeah. So one way of seeing it is that essentially you can make a state like this by just classical communication between two parties instead of requiring any bell pairs shared between them.
Yeah. Exactly. That's exactly where I was coming from. Yeah.
Okay. Right. So eventually, is the condition that PIs are all real numbers, real positive numbers between 0 and 1? Yeah, is that?
Yeah, so that they're exactly like classical probabilities. That's right.
All right. Thank you.
Yep. Okay, great. So for our purposes, the definition of entangled is just a state which can't be written in this separable form. And in an ideal world, we would like to find some criterion which gives me some calculable quantity, which is 0 for all separable states and non-zero for all entangled states, like the mutual information was for the pure state case. But essentially, it turns out that if I give you an arbitrary state, then it's an NP-hard problem to decide whether or not it's separable. So we're not going to be able to do this. But instead, we can define a new criterion called the PPT criterion. And essentially, the set of PPT states will turn out to be bigger than the set of separable states. But if you know that a state is not PPT, then you know that it's necessarily entangled. Okay. So let me define what this means. So essentially, what you do is you take the state rho A, and then you take a partial transpose of it in A2. So partial transpose just means that I essentially swap the bras and cats between, in the A2 part. So I send A2 to B2 and vice versa, but I don't do anything in the A1 part. Okay, so that gives me some new matrix. And in general, this matrix that I get by this procedure doesn't anymore need to have all non-negative eigenvalues. So it can have some negative eigenvalues. So if this state does have all non-negative eigenvalues, then I call it a positive partial transpose state. And in particular, you can check that all separable states of this kind are a subset of PPT states. Okay. So now for this PPT criterion, you can actually find a quantity called the logarithmic negativity, which tells you exactly whether or not a state is PPT. So the way you define this is just by taking the eigenvalues of this partial transpose and their absolute values, and then summing the absolute values and taking the log. Okay. So now the negativity or the logarithmic negativity being 0 is exactly equivalent to rho A being a PPT state. And this just means that if the negativity is greater than 0, then rho is necessarily entangled. Okay.
Hang on, sorry. So I understand positive partial transpose. So all the eigenvalues of this rho T are non-negative. Then you take the log of the absolute value, and if it's 0, say that again. I'm sorry to be slow.
Yeah. Okay, sorry, I can go through it more slowly. So you know that the eigenvalues of rho AT2 will still sum to 1 because this partial transpose doesn't change that. So because they all sum to 1, if they're all positive, then this quantity will just be equal to 1 inside the log. Or if they're all non-negative, then this quantity inside the log is always equal to 1. So you just get 0. But if it has any negative eigenvalues, then you're going to get something greater than 1 inside the log.
I see. Okay.
Right.
Okay. Thank you. I'll process that. Thank you.
Yeah,
Okay.
yeah. So the main point is that somehow you can treat this negativity, even though you can have states with zero negativity, which are still entangled. You can treat this as some kind of proxy for telling you whether or not the state is entangled. Okay, and the nice thing about it is that it can actually be calculated much more simply than most other entanglement measures for mixed states. So, so this is the quantity that we'll actually be calculating for much of this talk. Okay.
I see. So your E being greater than 0 is sufficient to ensure that it is entangled, your rho.
Yes, exactly.
Okay. Yeah. Okay. Thank you. Thank you.
Okay, great. So this slide is slightly technical, but
can I ask a question?
Yes.
So, what are the states which were included in PPT, but not treated just separately? As they still give 0. Yeah, they still give 0 epsilon, but seem to be not just separate.
Right. Yeah. So this is. So these states turn out to have bound entanglement. So that is one thing that's known about them. I'm not sure if there's a very sharp characterization that's known, but essentially, yeah. So I'll be talking more about what bound entanglement means later, and actually, this is a different set of states with bound entanglements from the ones that I'll be talking about, but they also have this property that somehow. So if you're familiar with entanglement distillation, which I'll be talking about in a minute, then those are states from which somehow you can't distill out bell pairs. So if that doesn't make sense, then I'll be talking about that in a minute.
Shreya, I'm sorry to be so slow, but I'm struggling with the following dumb thing. Suppose rho T2 had 2 positive eigenvalues, which were both half. Wouldn't log of mod lambda k be non-zero, even though it's a PPT state as per your definition? Because the eigenvalues are not 1 and 0. They're, some set of positive numbers which are all positive. Sorry.
You take the log of the sum.
Oh, thank you, Shreya. Sorry. Excuse me. Thank you so much. Excuse me. Thank you. I got messed up. Okay. Thanks. Sorry. Okay.
Yeah. No problem. Yeah. No, this is an important point, so it's good to.
Sorry, there's one more thing which I sorry, Abhijit, go ahead.
No, what is the relation between the eigenvalues of this the transpose matrix and the original one?
Yeah, that's a good question. In general, I think there is no simple relation. I think in the case where the state is a pure state, then you can write down a simple relation between the two. And then you can, because of that, you can relate the negativity to the 1/2 Renyi entropy. Okay. But in the general case, I think there's no simple relation that I know of.
I see. Okay.
Is it clear that the this rho transposed, which is obtained by transposing A2 and B2, right? I mean, it's so that thing still satisfies the trace condition?
Yeah, it still satisfies, yeah, because somehow this operation doesn't change the trace at all, because the diagonal elements are the same. So yeah, so that is still satisfied, but it's just that they do, now if you diagonalize this new matrix, then it doesn't have to have, yeah, it can have negative eigenvalues.
So are you saying that the rho T2 and rho have the same eigenvalues? No, you are not saying that.
No, sorry. They don't have the same eigenvalues, but they do have, I think just in this basis, if you were to look at the diagonal elements, then those would be unchanged. And so if you take the trace, then yeah.
I mean, okay, this transposing is a little unconventional to me. So yeah, okay, all right. So you're saying that it still satisfies the trace condition. That is to say, trace of rho T2 is 1. So it's if it has non-negative eigenvalues, the sum of all that is equal to 1 still.
Yeah.
And on the other hand, if there was anybody who was negative, then at least one eigenvalue has to be greater than 1 or something. And then you take the log of that stuff, and then you will find that. Okay.
But the log of the sum got wrong. It doesn't matter whether one eigenvalue is greater than one. It's just that if one of them is negative, then the sum of moduluses will be greater than 1.
Greater than 1. Yes, yes. Right. Okay, right. Okay, thank you. Thanks, Shreya.
Maybe you said this, Shreya, but is there a way to see it quickly that separable states will give you 0?
Yes. So that just follows directly from the fact that if you do the partial transpose in this sum, then you'll just be transposing the second matrix. So because it's just linear, so you'll just end up transposing the second matrix in each of these, and then I think so then that doesn't end up changing the eigenvalues.
The eigenvalues won't be changed, you say?
Mm-hmm.
I mean, you have to use somewhere that the p's are real numbers between 0 to 1. I thought that was important.
Right.
Okay, I mean, we can go ahead for now, but
I think it's also important that rho tilde A2 is an honest density matrix on A2. So, if you look at this in the...
Yeah, that's right. Yeah.
Yeah. If you look at you look at this row in the basis where rho tilde A2 is diagonal, then it seems clear that it won't do anything to the eigenvalue. Right? Is this right, Shreya?
If you look in the basis where each of these is diagonal.
Yeah.
Yeah, exactly. So that was an important part too. So maybe, that.
So, Onkar, are you saying that the fact that PIs are real number between 0 to 1 is not important?
No, that is also important, but it's also important that rho A1 and rho tilde of A2, they're both, they're all of these things are honest density matrices on A1, A2, and so on.
I see. Okay. Yes, thanks.
Yeah, great. Thank you. Okay. So, great. So now that we've established that, so this is the quantity that we want to calculate. But in order to actually calculate it, we'll be going through this other set of quantities. So this slide will be slightly technical because, but these technicalities end up actually being pretty important in the calculations that we do. So I want to spend a little bit of time on them. So we define these new quantities called partial transpose partition functions, where we take the trace of this partially transposed density matrix raised to some power n. And then we can also use these to define quantities called Renyi negativities, which are so I haven't written down the explicit definition, but essentially all you need to calculate them is essentially the partial transpose partition functions. And they're kind of analogous to the Renyi entropies. Okay, so once you define these quantities, then you can define a replica trick for calculating the negativity, where, so these quantities can have different behaviors as functions of n for even and odd n. So if you take the function that you get for even n, and then take the limit as n goes to 1, in both of these quantities, sorry, there shouldn't be a log here. Then so you can use that to find the negativity. But actually, in practice, it turns out that this analytic continuation method is not will not be useful in the finite temperature cases that we look at, because we'll find many situations where this ZNPT even for even n is not an analytic function of n. So it can be different functions for different n. Okay, So a more reliable method for using these ZNPTs to calculate the negativity is to go through a quantity called the resolvent, which is defined in this way in terms of rho AT2. And if you expand this definition, then essentially it becomes a sort of infinite series which involves these ZNPTs. Okay. And if you can calculate this, then you can see from this definition that you can find the density of eigenvalues of rho AT2 from the region where this resolvent becomes imaginary, somewhere on the real axis. So where it becomes imaginary, it becomes complex. So then in that region, the imaginary part will give you the density of eigenvalues of rho AT2. And once you found the eigenvalue density, then you can find the negativity from it just by definition, essentially.
Yeah,
Yep.
Sorry,
Yeah.
quick question. What does it mean that a function is not an analytic function of integer values?
Yeah, so I just mean that it's...
that you cannot easily find the analytic continuation? Or that
sure,
you can prove
yeah,
that...
Yeah, I don't know if you can prove that it's not analytic, but you definitely find that there are cases where just...
it looks very different for n equals 2 and n equals 3.
Yeah, exactly. So yes, like for instance, from the Renyi entropies, we're used to cases where like all n can be seen as some common function. Or the entropies can be seen as some common function for all n, but here you see that they just have qualitatively different behaviors.
But that could just be a lack of imagination.
For
right?
n equal to 2 and n equal to 3.
But couldn't that just be a lack of
In
imagination?
principle, yes.
I see, but it's just difficult to do anything with it. Yeah. Is that's
yeah.
take home? Yeah. Okay. Thank you.
Why do you insist on even n?
Yeah. So there's slightly there's just a slightly technical reason for that. So if you expand this in terms of the eigenvalues of rho AT2, then because there can be some negative eigenvalues, in one case, like if you take even n, then you'll be summing over something which looks like the sum of the absolute values of lambda I to the power of 2n. So you'll take the same sign for both the negative and positive eigenvalues. But if you were to take odd n, then you're taking you get a minus sign with negative eigenvalues.
Yes.
So if the quantity you want to end up with is like the sum of the absolute values, then you want to take even n and then analytically continue to n equal to 1.
Okay, thank you.
Yep.
Sorry, Shreya, minor point, but isn't there a log on the right-hand side of your last equation, if I understand right? Because it's log of sum of the absolute value.
Yes, sorry.
Huh?
Yeah.
Okay, sorry, just making sure I'm following. Thank you.
Yeah, absolutely. Sorry, that's a misprint. It should have been a log. Yeah.
So,
Can I ask a question?
Stupid.
Yeah.
So Abhijit, go ahead.
Okay, yeah. So just as general question. I mean, this is probably my ignorance, but when even in the Renyi entropy case, when one thinks of this as an analytic function of n, why can't just add some function of sine pi n or something like that, which goes to 0 at integer values? Does that not affect the von Neumann entropy? This is probably a bit outside, but it was just this issue was kind of similar.
Yeah, I don't know. I've never really thought about what that would do. I guess if you take...
Because
so
those
does that
just go to 0 on the Renyi's and then integers.
But
would it also go to 0 at n equal to 1?
Yes, sine pi n, yes.
Yeah. Yeah. So it shouldn't affect the von Neumann entropy either. At least that's...
You have to take derivative and so on, right? Over for one. I mean, okay, maybe it just doesn't matter. Sorry, I thought this was well known and someone would say, okay.
I had thought the answer would be that there are some properties that you in the complex plane about this function that you can establish that makes it unique given these integer values. As you know, Abhijit, in scattering amplitudes, something similar happens.
Right? Yeah. But yeah, usually one doesn't. I have not seen the discussion of this kind of.
Yeah, even I've not seen, but I thought that would be the answer.
I see. Okay, thank you.
I think there is something like this in that you compare the nearby rows, in taking the n going to one limit. And if the additional function vanishes for all integers, at least in some cases, it doesn't show up in the limit. Okay, but I don't know the exact statement, but I also think there's some statement like that. No, Shreya might know anyway. Yeah. Okay.
Yeah, I haven't seen any discussion of this, but it is an interesting question.
Yeah, okay.
Yeah, I'm not sure.
Thanks.
Hi, so can I ask a question? Hello?
Yeah.
Yeah, so at least in the normal replicated Renyi kind of entropies, was there something of this sort where you had to distinguish between odd and even ends?
Sorry, for Renyi entropies?
Yeah, in the normal things where you didn't really partially transpose and so on. Was there a distinction between even and odd cases?
Yeah, so no, in that case, there is no difference. And somehow, so here, the reason why you end up choosing even n is because you have negative eigenvalues, but in that case, because you're just looking at eigenvalues of the density matrix, they're all positive. So you don't have this kind of issue in that case. Okay.
Yeah, thanks.
Okay, great. Yeah, so the main takeaway from this slide was that these are the quantities that we calculate, but in many cases, it's not possible to use analytic continuation. And so the method that we'll actually use is trying to find the resolvent, which involves doing this sum. Okay. Okay, great. So yeah. Okay, so I introduced two measures called the mutual information and the logarithmic negativity. But those are not the most natural measures from an operational perspective for mixed states. So let me introduce what the operational measures are. So these are called the entanglement cost, EC, and the distributable entanglement, ED. And what you do to define these is to imagine some hypothetical setup where you start with some number n of EPR pairs between the systems A1 and A2. And then you imagine using just local operations and classical communication between A1 and A2. And you want to use those in order to construct your actual state rule. Okay. So if you want to do this, then there will be some minimum number of EPR pairs n that you need in order to make rho. And we call this minimum n the entanglement cost. So the actual definition is a little more technical. It involves sort of taking a large number of copies of these two systems and taking the limit where the number of copies goes to infinity. But intuitively, the idea is that you're looking at this process of forming the state from EPR pairs. Okay. And then you can also imagine the reverse process where you start with this state rho, and then you want to use the same set of local operations in classical communication and convert it into some number of EPR pairs. So this maximum number that you can get by such processes is called the distillable entanglement, ED. Okay, and one reason why the entanglement entropy is such a natural measure to use for pure states is that for pure states, for both of these processes, both the cost and the distillable entanglement are equal to the entanglement entropy. Okay. But for mixed states, this becomes much more complicated because in general, you find that the entanglement cost can be larger than the distillable entanglement. So this process can be quite irreversible. And in general, neither of these quantities is equal to the entanglement entropy. Okay. And both of these quantities are very hard to compute, even if you have some few qubit system. So this is the reason why we don't use them and we use things like the logarithmic negativity instead.
Mm-hmm.
And
So sorry to interrupt. You should go on. I mean, the fact that neither is equal to S rho, I mean, that's sort of, I think, intuitively clear because the Shannon part, the pi log pi part won't be reflected in the number of bell pairs, say you can distill, etc. But why is, to me at least, maybe you can say if my thinking is right, but why is EC greater than equal to ED? I'm not sure I fully get that. That is, I might have thought that that say any attempt to define a von Neumann entropy between the two sides would yield a result bigger than the number of bell pairs you can distill, because there's a classical part to that von Neumann entropy. That you don't get something which equals the number of bell pairs, I understand. But why is EC bigger than ED? What's the intuition there? Sorry, I'm missing this. You need more bell pairs to be able to extract the required and the amount of, to prepare rho, which means you also have to prepare the pi parts of rho, right? Maybe this is the point, perhaps. Is it? I mean,
yeah, I'm not sure if I understand very intuitively in terms of the pi part why it's irreversible.
Okay. Okay. No, just in case. Okay.
Yeah. It would be nice if there was some more intuitive way of understanding it, but I think it's just in practice they just find when they calculate these things, even for simple examples, that EC can be bigger than ED.
I see. Okay. Yeah.
But
thanks.
just to understand, in particular for separable states, these things are zero, right? Like the EC and ED are zero for separable states?
Yeah, exactly. So we said earlier that was essentially one way of seeing that that separable states are not entangled, because somehow you don't need any bell pairs in order to prepare them. You can just use classical communication.
Right.
Yeah.
Right.
And what about these PPT states? Is there some statement there?
Yeah. So for actually, so I was going to I also wanted to mention that you can have another set of transformations that you can consider instead of LOCC, which is the set of PPT preserving transformations. These are just defined as transformations which, if you give a PPT state as an input, then the output is also a PPT state. And then under this bigger class of operations, again, you can consider the cost, like the minimum number of PPR pairs that you need to prepare the state, and the distillation. And these will in general be different from the LOCC versions, which are EC and ED. So I think, so for PPT states, definitely, yeah, so we said earlier that, let's see. So yeah, so I think that I'm not sure.
Yeah, it's fine. We can discuss this later after. Yeah. Thank you.
Yeah. So for so one thing that's definitely true is that under PPT operations, the number of states that you, like the set of states that you can distill, is just the whole set of PPT states. So there are no PPT states. It's like there are no bound entangled states under PPT operations. And then I don't remember if there are some known statements about what happens to PPT states under LOCC operations.
Okay, great.
So maybe there is some simple statement that I'm forgetting.
Great. Thank you so much.
Sorry, just once, separable were those states of the type you wrote down, right? Pi, rho, cross, tensor product rho. Is that correct? What is separable? Sorry.
Yeah, exactly. Those were separable states, and those will have 0 EC and ED.
Yeah, that I can see. But somehow anyway, you should go on. What's counterintuitive to me is that you can create the state rho, but you need more bell pairs than you can extract out of the system. This is okay. Anyway, all right, go ahead. Very interesting.
It is a very strange it is a very strange fact. And in fact, what we'll be showing, like what we showed in this paper, and what we'll be talking about is that that these situations are actually pretty generic, where you have this kind of irreversible state. Okay, so so the way that we'll show that is by using certain inequalities. Between.
Sorry, Shreya. So maybe you said it. What is LOCC?
Oh, sorry. So LOCC just means local operations. So operations which are local to either A1 or A2, and classical communication between them.
What does it mean? In terms of Hilbert spaces, what is this classical communication thing? I mean,
classical communication.
Can I understand this as some kind of sequence of unitary operations, or?
Yeah.
What am I doing? What am I doing on the top row? What am I doing from the left to the right?
So I think the local operations just means that you can do operations which are the identity on one of the systems and something non-trivial on the other one.
Okay.
And I think the classical communication part means that you can send messages that are like one classical bit from one system to the other, but you can't transfer some quantum state from one system to the other.
Okay.
Can I just add one small thing to what you said, Shreya? If you don't mind, that might help. Which is, let's include in local operations, Gautam, unitary transformations that can act on either A1 or A2, as Shreya said.
Got it.
But also measurements, projections. Okay.
Yeah.
Now, suppose you carried out a measurement on A1 and you got a result. The classical communication part allows you to call up your friend in A2 and tell him or her the result you got out of a measurement. So that's the additional communication part, but it's an exchange of a classical bit or a phone call, if you like, that you get out of operations, including measurements and unitaries on one half of the system. Okay. Anyway, I just thought I'd add that, but that sort of helped me understand the communication part when I studied it.
Okay, right. Thank you. Thanks, Sandeep. And thanks.
Sorry, just to understand, LOCC does not change for pure system the entanglement property, right? But for mixed entangled system, LOCC, you're saying it would change the entanglement. Is that the point? For pure entangled state, LOCC should not change the entanglement between the A and B, but for mixed system, mixed separable system, it does not change, but for mixed entangled system, it would change the entanglement. Is that the point? That's why you got EC and ED to be non-zero for
to be not equal to each other. Yeah,
and also not is equal to 0. For pure entangled system, I would suppose EC and ED both are 0, right?
No. So they're both equal to the entanglement entropy.
Both, yeah, and entanglement should not change, right, under LOCC, right?
Yeah, exactly.
But for mixed entangled system, you're saying that it would change under LOCC. Is that correct?
Yeah, I think that makes sense because I think that should follow from this, right? Because you start with something which has the entanglement entropy of n EPR pairs, then you go to this state using LOCC. And then you go from here to some number of EPR pairs, which is smaller. So it seems like you change the entanglement entropy in this process.
I see. And PPT can PPT be considered as local operation?
No. So LOCC is a subset of PPT. PPT preserving transformations. But in general, the set of PPT preserving transformations is bigger.
Okay.
Which is why you get a different set of entanglement costs and distillable entanglements. So for this reason, the costs will in general be smaller for LOCC than, for PPT than LOCC, and the distillable entanglement can be larger because it's a more powerful set of operations.
Okay, thank you.
Yeah.
Just one question, if I can ask.
Yeah.
So you mentioned here that this entanglement cost and distillable entanglement are hard to compute. So I presume this is because, so is there any known way of relating these to the density matrices for A1 and A2 or any the eigenvalues of these, or is there any direct connection between these, any known connection?
No, I think in general there isn't, and that's exactly why they're hard to compute. So they've only really been computed in very special cases of a few qubit systems.
Thank you.
Yep. Okay. Great. So we can't directly use these quantities, but what we can do instead is use the quantities which we can calculate, like the negativity and mutual information. And luckily, these have some connections through upper and lower bounds to these operational measures. Okay. So for this talk, we'll be using two things. One is that, so another sort of technical point is that you can define, in addition to everything that I defined here, you can define also exact versions of each of these costs, which is just essentially a different way of taking the limit of, so I mentioned that the actual definition of these things involves some limit of a very large number of copies of the systems. And when you're taking that limit, you can either take the error in this preparation to vanish as the number of copies goes to infinity, or you can take the error to vanish before taking that limit. And so if you take the error to vanish before taking that limit, then you can define exact versions of these costs. And so the exact PPT entanglement cost turns out to be greater than or equal to the logarithmic negativity. Okay, so it's okay if you don't understand the exact definition of this exact part. It's just some slightly different technical version of the same thing that I described on the previous slide.
But since you said it just once, I understand usually the definition of distillable amount and so on involves taking n copies and working in the asymptotic limit. And here you're saying do take the n copies and then before you take the asymptotic limit. Is that what you said? To define?
Yeah. So when you take this asymptotic limit, then you can do two things. One thing is you can say, okay, the distance between whatever I prepare from this and rho has to vanish in the limit that n goes to infinity. Or you can say that you don't want there to be any error. So you just require exact preparation and then take the limit that n goes to infinity.
Okay. And that's the exact version. Huh?
Yeah, exactly.
So you don't want any error. Okay. Sorry. Thank you.
Yep. Okay. So this quantity can be related, and the negativity essentially gives a lower bound on it. And the mutual information, even though we said it contains both classical and quantum correlations, it is useful for understanding the entanglement structure because it's related to the distillable entanglement. So it's greater. So 1/2 of the mutual information is greater than or equal to the distillable entanglement. Okay. So in particular, this means that if we find situations, as we will, that where the negativity is much bigger than half of the mutual information, then that means that the exact entanglement cost is much greater than the exact distillable entanglement. Okay. So
sorry, Shreya, for a pure state, what is the connection between the mutual information and the distillable entanglement?
So for a pure state, I guess because the distillable entanglement is just the entanglement entropy, and the mutual information is twice the entanglement entropy, so this is just saturated.
Okay, so this is saturated. So the half was there even for the. Thank you.
Yeah. Great.
I mean, there SA and SB or SA1, SA2 will be 0, and the von Neumann entropy will be in the entire distillable number of qubits.
And sort of this inequality is capturing the classical part, right? That this mutual information is greater because there's also the P log P. in that
mutual. That's a good way of understanding it.
Thank
That's
you.
right.
Yeah, there's extra Shannon stuff. Go ahead.
Right. Great. Okay. So so this means that, if we find a situation where the negativity and mutual information have this relation, then the preparation of the state from EPR pairs is a highly irreversible process. And sometimes such states are said to have bound entanglement because somehow they have some entanglement, but you can't get it out and turn it into EPR pairs. Okay. Great.
If I may just ask, so this is a bit like defining the free energy of the system, right? In the sense that the free energy measures the amount of useful work that you can extract from the system. So in same way, bound entanglement measures how much free entanglement or the opposite of that, how much free entanglement you cannot extract from the system.
Right. Yeah. I mean, it's possible that you can do something else with it. It's just, but if you phrase doing work in terms of
extraction of EPR pairs.
Yeah, then that's certainly true.
Thanks.
Yeah. Right. Okay. Great. So that was all the background and setup. So now I'm going to talk about entanglement phase diagrams. So I'm going to talk about first, just as a reference case, the infinite temperature case, and then I'll talk about our results.
So sorry, Shreya, keep slowing it down, but just bottom line is for a general mixed state, then the cost, entanglement cost is bigger, will be bigger than the number of bell pairs you can finally distill out. That's the bottom line, right? From using this measure and all that. Okay.
Yeah, that's right. And in some cases, you can even use these calculable quantities to deduce that it's irreversible.
Okay. Thank you.
Yeah. Okay. Great. So then let's return to the question that I mentioned many slides ago, which was just.
I have a question. So your definition of bound entanglement here is different from the one you explained earlier, right? The one where negativity is 0 and still the state is entangled. That was what you called bound entanglement earlier, right?
No, so okay. So the definition of bound entanglement is always that the entanglement, like that the distillable entanglement is close to being 0, but the entanglement cost can be large, or non-zero. So one way in which that happens is, and actually, so I think those might only be bound entanglement. So sorry. So the states that I mentioned earlier were the states where negativity is equal to 0. And that is one way in which you can have that, but this is a different way in which you can find bound entanglement.
Okay.
Yeah, but it's true that these states are not the ones that I was mentioning earlier.
Okay, thank you.
Okay, great. So the question we want to ask is, like I said before, about how you consider some mixed state rho A, which is macroscopically thermalized, and you want to ask how much entanglement there is between A1 and A2. And the setup that we use for studying this question is to introduce some auxiliary system B and consider a pure state on the full system AB. Okay, so this is a very natural thing to do, especially in the black hole example, where if A is the radiation, then B is just the actual black hole. Okay, so like Paige, the first thing that we can do is just consider some finite dimensional system AB and consider random pure states in AB with the uniform measure. Okay, and then we can ask about what form these quantities like the logarithmic negativity and Renyi negativities and mutual information take. And we can ask what form they take as we vary 2 parameters. So essentially, the only 2 things you can vary here are what is the size of A1 relative to the full size of A, which we quantify with lambda, and what is the size of A in the full system AB, which we quantify with some parameter which we call C.
Size means dimension of Hilbert space. Is that right?
Yeah, exactly. So here I'm saying volume, where I'm assuming that the system is uniform, but more generally you can say like the log of dA1 over log of dA. Similarly here.
Okay.
Yeah.
Sorry, this system B can be arbitrarily small, or it has some restriction on B that it has to be a particular form?
So it can be, so we'll be considering all possible sizes of B, ranging from 0 to being the full system, or close to the full system. Yeah. Okay.
Sorry to interrupt again, but what are these A1, A2, and B in the context of black hole and radiation?
Yeah. So in the black hole example, you want to imagine that A1 and A2 are both parts of the radiation, and B is the black hole. And then, so the question we're asking is, what is the entanglement between two parts of the radiation? Okay.
Like say early radiation and then a little bit that came out later, right?
Exactly, yeah. So then, in the black hole case, then you can see varying these parameters as a function of, like you can see varying the parameter C as a function of how much time has passed in the evaporation process. So C equal to 1/2 will be something like the page time. Okay, so as we vary these two parameters, we find that there are 3 different qualitative forms that the negativity and mutual information can take. Okay, so first you can just imagine taking C to be less than 1/2. So this system A is less than 1/2 of the full system. And in this case, we find that the negativity is just 0. Okay, and this is essentially happening because A1 and A2 are both entangled entirely with B. So there is no room left for entanglement between them, okay, because of the monogamy of entanglement. Okay, and then you can also imagine a case where A2 is bigger than the combination of A1 and B. And in this case, you find that the negativity is just proportional to the number of degrees of freedom in A1. And essentially, this is happening because now all the degrees of freedom in A1 and B are both entangled with A2. So that just simply explains why it takes this form. And then sort of in this in-between area where you don't have that any of the systems is bigger than the combination of the other two, so they're all kind of roughly of the same size, you find this other form, which looks like the difference in the number of degrees of freedom of A and B divided by 2. Okay, so an intuitive way of understanding this is that essentially sort of log dB of the degrees of freedom in A are used up in entanglement with B, and then whatever is left is used for entanglement between A1 and A2.
Right.
So one thing that is interesting about this is that here within this regime, the negativity doesn't depend on the individual sizes of A1 and A2, it just depends on this combination. Okay. So these are 3 different qualitatively different forms, and we call these entanglement phases. And another thing that is that should be noted about this random pure state case is that here all the different quantities Z and PT for all n, Rn for all n, and the negativity and mutual information all have the same phase diagram. Okay, and in particular, the mutual information will just be 2 times the values of the negativity in each of these phases. Okay, so essentially, all of these quantities seem to be reflecting this relatively simple picture, and they seem to be reflecting the same physics. Okay. Great. Any questions about this?
I see.
Shreya, on the right-hand formula, the E of A1, A2 is a half of something. Why is there a half? I mean, why is there a half in that thing?
So it's not immediately obvious, but I think if you try to count, sort of, if you were to entangle log dB of the degrees of freedom in A1 and A2 with B, then you would take some number out of A1 and some number out of A2. And then if you try to find the most efficient way of doing that, then in the end, you're left with sort of 1/2 of this.
There's some optimization going on here. Is that the thing?
So in practice, I mean, what is actually happening in this state is probably not this kind of sort of bell pair picture where you only have bipartite entanglement between the two systems, but this is one way of trying to understand, or like one thing that can, like, if you try to do that kind of optimization, then it accounts for this kind of structure.
Yeah, so it's not assumed that A1 and A2 are of the same size, right? This
No,
half has nothing to do. Half has nothing to do with that.
No, it's not assumed that they're at the same size.
I see.
So as long as you're in this regime, so they're of the same size only here, right? Along this lambda equal to 1/2 line.
Yes.
Yeah. So that's why it's called. So that's why this is called the entanglement saturation regime, because somehow as a yeah, if you're at the same value of C, then as a function of lambda, the entanglement just seems to saturate if you go along this line.
Thank you.
Yep.
So yeah, question. This uniform measure on this ensemble of pure states to begin with, if I think of choosing a state and getting other states by acting with unitary transformations, then is it analogous to the Haar measure on the unitary group?
Yes, exactly. It's exactly the Haar measure in the unitary group.
Thank you.
Yep.
So, sorry, Shreya, you've said it in words, but just the picture which seems to be coming out from these sort of calculations, very nice calculations of yours, is that basically, if you had A1 and A2 to be entangled with B, then that entanglement with B limits, in a sense, the amount of mixedness between A1 and A2, right, which can be allowed. That is, as measured in your epsilon parameter, right? Because anyways, some of the quantum correlations are soaked up by the entanglement with B, and then the remaining ones which can be allowed subject to the constraints of monogamy or whatever can only do so much by way of jacking up your this epsilon measure, isn't it? I mean, that seems to be the case.
Yeah, exactly. So in all of these cases, you can just understand it in terms of entanglement with especially in these two cases, you can understand it in terms of everything being entangled with the largest system, and then because of monogamy of entanglement, there's no room left for any other entanglement.
I see. Very interesting. Okay. And some of the partial trace, whatever that whole thing of reversing half, it sees this in a very, very nice way. Huh?
Yeah, exactly. And somehow these calculations are telling you that you didn't need to even do the partial transpose, because the mutual information would actually give you the same information.
Would also capture it. Okay.
Right.
So does that mean that the negativity minus half the mutual information is just vanishing in all cases?
Yeah, in this infinite temperature case, that's true.
Oh, I see. So there's no bound entanglement at all.
Yeah.
Or well, maybe that's too quick, but okay. At least that measure is zero. Okay.
Yeah. So this is not the case where we saw bound entanglement.
Got it.
Yeah. So actually, so this calculation was first for random pure states. It was first done in this paper. Okay. So what we wanted to do was to.
Sorry, yeah. Why did you call this infinite temperature case? Is it because of the measure that you are using?
Yeah. So there are a few different ways of seeing that it's the infinite temperature case. One is just that intuitively, because you're averaging over all random pure states, you're not taking into account any energy conservation constraint. And so the most natural thing to expect is that they equilibrate to infinite temperature. And when you calculate entropies or negativities in this, they're always proportional to this log of the dimension, which is kind of like what you would expect if you had the just the infinite temperature, like the maximally mixed state on the system. Yeah. So what we now want to do is find some way to generalize from this infinite temperature case to more realistic situations, which you would see in systems like continuum systems like QFTs, and also in discrete systems, if you impose energy conservation, then in general, you expect that the equilibration is to some finite temperature. Okay, and to study these cases, we'll use this equilibrium approximation technique, which we developed in this paper from last year. So I think Hong actually gave a talk at TIFR about a year ago about this paper where he described these techniques. So what I'm going to do in this talk is first just talk about the results that we get from using this method. And then if there's time, I can talk about the method that we actually used. But essentially, it's a simple generalization of what was done in this paper for the entanglement entropy to the negativity. Okay. So at finite temperature, in general, we'll use two new parameters, which we'll call lambda and c again, and they're just natural generalizations of the ratios of the logs of dimensions that I defined earlier. But now in terms of the entropies of the equilibrium density matrix. Okay, so essentially in all finite temperature cases, I'll have in mind some kind of equilibrium density matrix, which is macroscopically describing the equilibrium that I'm in. And then I can consider finding the entanglement entropy of that matrix in different regions. And so I can take the ratio of the entropy in A1 and A, and I call that lambda. And I can take the ratio in A and the full system AB. And these should just, so if you have some homogeneous system, so okay, yeah, so I should also mention, so in general, you can expect that A and B will reach different kinds of equilibrium, because you can imagine they interact for some time, and then they could be separated so that they could reach different equilibrium states, okay? So if the system is homogeneous, then in those cases, these will again reduce to just the volume ratios. But more generally, you can have some, sort of these parameters will give the natural generalizations of lambda and c that I defined earlier. Okay, so good. So now the thing that is different at finite temperature is that each of these infinite number of quantities, so the mutual information, logarithmic negativity, and all the different Zn PTs for different n, each of them will have a distinct phase diagram. Okay. So yeah, so first let's just try to discuss what the phase diagram looks like for the mutual information, because that's the simplest thing to calculate. And for that, we don't even need to generalize the methods of this paper. We can just directly apply them, because we just need to calculate entanglement entropies. Okay, so let me just remind you.
So, sorry, Shreya, just one thing. This S equilibrium, I mean, this rho equilibrium, how exactly is it? I mean, you said you compute S through rho, but how exactly is rho defined? Just once more, it's not quite a thermal density matrix, right? At some temperature T for the subsystem of interest. Because that's right. Nothing interesting, I suspect. I mean, I don't know.
Yeah, exactly. Yeah, so the general idea behind what we're doing here is that indeed the state rho that is obtained from the actual time evolution is not rho equilibrium, and that's why it has some interesting entanglement properties. But we still expect that because this rho equilibrium macroscopically resembles rho, you should still be able to give some expression for the these quantum information theoretic quantities like entanglement entropy and negativity in terms of rho equilibrium, even if it's not exactly the entanglement entropy of rho equilibrium.
I see.
So that was kind of, so in order to try to find some expression like that, that was mainly what we did in this paper.
I see.
Yeah.
Okay. Yeah. No, please go on. I think it'll get clearer in my head as you discuss it more. Yeah. Go ahead, please.
Yeah. So it should be. Yeah.
Sorry, Shreya. And you're looking at a particular density matrix on this whole system, or somehow it's generic. I haven't understood. The earlier context was this random matrix, which I understood. Here, I haven't understood what state you're considering here.
Yeah.
Yeah, exactly. So no, I'm not considering a particular state, but so I'm trying to describe a state. So the answers that I get will end up depending only on properties of this row equilibrium.
So you're considering a class of states?
Yeah, exactly. So you can imagine this specifying this row equilibrium as specifying some universality class of thermalized states at late times, which we expect should all have similar, even though their details will be very different and they're obtained by very different time evolutions from specific initial states. Somehow we expect that because of this general principle of equilibration, it should be possible to describe all of them with some universality class.
I see. And the properties of this class go into your actual calculations.
Yeah, exactly. So, and that is all in the choice of this equilibrium ensemble.
Okay, thank you.
Yeah. Yeah. That's a really good thing to clarify, because I think this can be a slightly confusing point.
And sorry, and is there some sort of modified matrix model you're looking at? Or?
No, somehow it's not. Yeah, it's just a sort of general method for trying to extract, like basically it just involves trying to project in a physically motivated way in the expression for the time evolved entropy. And somehow that projection depends on properties of rho.
Thank you.
Yeah. So that will probably become clearer eventually. Okay. So good. So let me just quickly remind you in one line what Page did in his calculation while finding the von Neumann entropy for random pure states. So he just considered some general state of this form with the Haar measure on some combined system R bar. And then it turned out to be the case that if you average the entanglement entropy in R and R bar, then both are equal to the minimum of the log of the dimension of R and R bar. Okay. So a natural generalization of this to finite temperature is just to say that you take the that both are equal to the minimum of the entanglement entropies of the equilibrium density matrix in R and R bar. Okay, and this is something that is very natural. And for instance, it was used in a paper by Page where he tried to estimate realistic realistic Page curve for actual black holes. So we were able to sort of derive this expected generalization using the equilibrium approximation. Okay, and this is just a slightly technical point about how we did it. So what we actually calculate in the equilibrium approximation are these Renyi partition functions, which are these quantities, which involve taking moments of the reduced density matrix. And we find that for these quantities, it's always the case that you end up taking the minimum of the nth Renyi entropy of the equilibrium density matrix in R and R bar. And then you can make arguments with both analytic continuation and resolvents to see that this is actually true in a lot of cases. Okay.
Sorry, Shreya, let me just try to make sure I understand. So first of all, you're going to choose, let me see, I'm still, so let's say you take your full system of 3 parts, A1, A2, and B, let's say, then you choose the density matrix of the whole system from some class which you call the equilibrium density matrix. Is that right? And then you trace, or what is, I'm a little lost. There's some class from which you draw your density matrix and you call it the equilibrium density matrix, right? Which I haven't quite understood. It's not e to the minus beta h, but some class, depending on your time evolution or something. Is that right, first of all?
So this thing which I'm calling, like in all the equations, this thing that I'm calling rho equilibrium, this is something like e to the minus beta h.
Oh, okay. So it literally is okay. So that's e to the minus beta h. Okay. And then go to the next slide again, just once more. And now when you say something like, okay, S rho R is the minimum, So I understand the right-hand side because you've chosen the equilibrium for R and R bar and computed the entropy. And for rho R, the left-hand side is computed on what density matrix? Just one, sorry.
Yeah, so this is the density matrix that I'm saying has macroscopically equilibrated to rho equilibrium, but actually it's a pure state, so it's definitely not equal to rho equilibrium.
Okay, so you have some other way of generating this, say through some time evolution or something you'll come to, and then you compare the entropy there. And okay, and what is the statement again then that for a thermalized, so go ahead. So then you find that the entropy of rho R is the minimum of these two.
Okay. Yeah, so one way of seeing that this rho R is not the actual equilibrium density matrix is that you have this minimum and not just the first thing, right? Because that, so this is kind of the philosophy behind it, that we want to find some expression which only depends on the equilibrium density matrix, because we think that details shouldn't be details of what the state rho is should not be important at late times. But at the same time, it can't actually be equal to the entropy of the density matrix because of unitarity. So this is the answer that was always expected. And then we were able to provide more justification for this based on this method.
Got it. Okay. Thank you. Okay.
Yeah, great. Okay, so if we use this expression, then we can immediately use it to calculate the mutual information, which just involves a sum of quantities like this. So so in this setup, we can just take R to be each of the different systems, A1, A2, and A. And then if we calculate the mutual information using this, then in terms of these new parameters, lambda and C, we find that we get exactly the same phase diagram as we got at infinite temperature. Okay. So the transitions happen in the same places. And if you look at the values that the mutual information takes, then those are also kind of natural generalizations of what you get in the earlier case. It's just that you replace logs of dimensions with entropies in all cases. Okay.
And sorry, I'm a little slow here, but in your previous slide, I thought you were taking RR bar together to be a pure system, but maybe not, right? Is that? I mean.
Yeah. So here, so remember, so I said that I added this auxiliary system B, and now the state on the whole system is a pure state. So now if I take R to be A1, then for R bar, I get A2B.
Oh, I see. Okay.
Yeah. So then when I do this minimization, then I get essentially these 4 different cases.
Okay. I understand. I understand. Okay. Thank you.
Okay, so this is nothing surprising, and in particular in this black hole example where we take A to be the radiation, then C equal to 1/2 just corresponds to exactly the page time at which the entropy changes from its increasing to decreasing behavior. Okay, so that is the same time. So essentially, by looking at the mutual information, we would conclude that the radiation starts to become correlated after the page time. Okay, but now the phase diagram for these Z and PT quantities becomes much more intricate. So for each n, we do get finite temperature generalizations of the 3 phases that we had at infinite temperature. But the thing that changes now is that the transitions become dependent on this index n. So for instance, here I've taken the canonical ensemble at some finite temperature, and essentially, so I've shown here R4 in blue. Okay, so here in this region, you'll get the ME phase for R4, and this region in the middle, you'll get the ES phase. And similarly, you get similar regions for R6, but the regions are now different for different n. Okay. Yeah, and even if you look at all n together, the structure is pretty complicated. Oh, also, so I've shown this black line here to compare with the earlier case. So essentially, the black line is the phase diagram for the mutual information. So essentially, so if you look, so essentially in this region, from the perspective of the mutual information, you're in the ES phase, but from the perspective of all the Renyi, like all of these Z and PT quantities, you seem to be in the ME phase, okay? So somehow the different quantities are reflecting different physics. And the really important thing about this diagram is that the analytic continuation is no longer reliable for finding the logarithmic negativity now, because especially if you look at sort of these regions where different ends have different behavior, then it's not clear how to analytically continue or whether it's reliable. Okay.
But sorry, Shreya, sorry to keep asking this.
Yeah,
just make sure. I mean, when you are doing, say, the PT calculation, okay, let's say we take A1, A2. Now, I'm not fully sure I've understood what exactly you have done. So you take, I mean, where is rho equilibrium coming in here? Are you doing the, I mean, what I would understand is that you relate the full density matrix of A1, A2, and B through some general unitary and average over that, but that's not what you're doing. So just tell me once more how you generate the rho, say, for A1, A2 to compute its Z and PT. Just once more. Sorry to be so slow.
No, I haven't explained that at all, but I could, could try.
No, I don't want to throw you off course, and I know we've already asked you a lot of questions. So just to understand, so there's some way in which you are generating a density matrix, huh? Through some evolution or something.
Yeah. So we're not really generating the density matrix. We're directly using an approximation inside these Z and PT quantities.
Okay, and just tell me that approximation once more. So just once more. Sorry.
Yeah. So that involves. So maybe I can very quickly sort of,
or just in words if you like, just so that because I didn't fully
so essentially, so there's some so you can imagine having some kind of path integral representation for this quantity from the time evolution. And what we do is essentially a projection. So then we motivate that some subset of configurations in this path integral should be stationary configurations. And we do, so essentially, so that this expression can just be rewritten as some transition amplitude on n copies of the system.
I see.
So this is just a rewriting of this expression. And then what we do is that we define a projector inside this expression, which depends on rho equilibrium. And then that essentially gives me an expression like this eventually.
I see.
Which some different permutation and it involves, so for one of the permutations you just end up getting simply the actual equilibrium Z and PT in rho equilibrium, but then give you other contributions.
I see. Okay.
Yeah. Okay. So that was a very quick.
No,
so
that's
it wasn't
fine.
really even an explanation.
Yeah. Okay. Thank you.
And then and we have some ways of trying to justify. Okay, great.
Sorry, Shreya, this configuration that dominated the path integral, that broke the replica symmetry. Did it break the replica symmetry?
Yeah, that's a good question. So some of them will. It turns out that in this ES phase, the thing that you get is replica symmetry breaking.
And is this calculation secretly some holographic calculation?
No, it can be turned into a holographic calculation in some cases.
Okay.
But it should be more general than that. It should just apply to any quantum any-body system, even if it doesn't have a gravity dual.
And what is the parameter that controls the approximation? I mean, what justifies the approximation? The size of the system, is it?
Yeah, exactly. yeah, so that series of projections that I showed to you is only justified in the case where you assume that the Hilbert space, like the effective Hilbert space dimension is large.
Thank you.
So like if you calculate the trace of e to the minus beta h, then that should be large, for instance.
Yeah.
Yeah. Okay. So yeah. So the main point of this slide was that because of this n dependence of the phase transition lines, the analytic continuation is no longer reliable. Okay. Okay. So because the analytic continuation is not reliable, we have to calculate the resolvent. And in general, this is a difficult thing to calculate because it is essentially, I showed you that it involves this infinite series over Z and PT. But we can do it in some special cases. So one special case where for some reasons which are just an artifact of the calculation, it becomes simple is when you take the microcanonical ensemble, but with energy conservation between A1 and B. Okay, so it's not the most physically motivated example, but it turns out to make the calculation doable in all regimes of lambda and C. Okay, so here, so what we see for the Renyi negativities is very similar to what I showed you in the previous example, where there's this n dependence in where all the different transitions happen. Okay, but for each n, you have these generalizations of the infinite temperature phases. But in the logarithmic negativity from the resolvent calculation, you see some interesting features. So I've shown these regions which I've marked with the same colors as before and called ME, ES, and NE. And these are just these turn out to correspond to analytic continuation of the phases in the Renyi negativities. Okay, so they're not exactly in the same regions as like they don't correspond to anything. The regions where you get these phases seem to have nothing to do with these lines in the Renyi negativities. But you do get, like, if you look at the expressions, then those are analytic continuations. But one interesting thing is that in addition to that, you get these two new phases, which I show in red and blue. And these are actually not, they don't correspond to analytic continuation of any of the phases of Z and PT. Okay. And another interesting thing is, so I've also shown in these dashed lines the transitions for the mutual information, and these seem to have nothing to do in general with the transitions that happen in the negativities. So somehow here, the logarithmic negativity and mutual information are reflecting completely different physics, except, so these two transition lines coincide, but somehow that is an artifact of the specific, we expect that that's an artifact of the specific model that we're using. Okay. Good. So any questions about this? Okay. Great. So now we can, it's useful to just consider, say, going along some vertical line in this diagram and looking at what forms the negativity and mutual information take. Okay, and I tried to mark these lines to show where all these different phase transitions are happening. So one interesting thing is that for the negativity, so initially it's 0, then it takes the ES form in this regime, and then it goes into this phase. It goes into this phase where you don't see any discontinuity in the first derivative. But then if you plot the first derivative, it's pretty clear that there is a discontinuity in the second derivative. Okay, so somehow these transitions are slightly different from like this, whereas this transition along this line is a first order transition. It's the second derivative that's changing in these new transitions with the new phases. Also, so this is really the key thing that I wanted to emphasize in this talk. You see this regime kind of between, like outside the yellow region, but below the dotted line, where the negativity is extensive, while the mutual information is sub-extensive. So it's never exactly 0, even in this region, but it's just not proportional to the volume. So we only have access to the volume contribution from our calculation. Oh, sorry, my internet, it says that my internet is unstable. Can you still hear me? Okay.
Yeah, you went in and out briefly, at least for me. I'm not sure. But
we can hear you
yeah,
now.
more
Sure.
Okay. Okay.
So, sorry.
Okay. Sorry.
Yeah.
So I was, I think I was. Sorry.
No. Go ahead. Since we are pausing, I had one, just a very rudimentary question again, if whenever you like.
Yeah.
Okay.
Yeah, of course.
So just I'm not as clear as I should be on the various measures which you're plotting. So once again, sorry, Rene negativity was the n going to 1 limit of the ZNPTs. What was Rene negativity? Sorry.
No, sorry. I think so. I didn't write down the expression for the Rene negativity.
Sorry,
just because I did. Yeah, sorry. I think my internet is still not great.
Okay.
Okay, sorry. Yeah, but for the Rene negativities, I didn't write down the expression. But it's essentially.
Okay.
It's defined in terms of like taking a ratio of Z and PT with the Rene partition function in A. And then taking the log.
Okay.
Yeah. Anyway, it's just some other quantity.
Okay. Go ahead.
Okay. Yeah. So am I still coming in and out, or can you mostly?
We can hear you now. We can mostly hear you. Yeah.
Okay. Good. Fine. Okay. So the main striking thing about this diagram is that you see this regime where the negativity is extensive, but the mutual information is sub-extensive. So you can also see that in this plot that the negativity starts increasing before the mutual information starts increasing as a function of C. Okay. Yeah, and also so this yeah, and essentially this turns out to be something that we also observe. So like I said, so this is the only example where we can calculate the phase diagram in all regimes. But in some other universality classes, we can calculate it kind of in the regime that corresponds to the NE and ES phases and the transition between them. And from those, we're able to verify that, again, the transition from NE to ES happens before the transition in the mutual information. Okay. So this fact that you see a regime where negativity is extensive and mutual information is sub-extensive seems to be sort of not just specific to this case, but a pretty generic feature of finite temperature. Okay.
Right.
Okay. So what does this mean? So this is quite surprising based on some of the things that I said before, right? Because if indeed the mutual information captures both classical, like all of both classical and quantum correlations, then when the mutual information is small, we should also expect that the negative, that there is no extensive entanglement in the whole state. But this turns out not to be true when we look at the negativity. Okay. Okay, so what does this mean in the black hole case? So recall that at infinite temperature, we found that both the negativity and the mutual information become extensive at the same time that the entropy starts decreasing, which is the page time TP. Okay, but what we seem to be seeing at finite temperature is that while the mutual information still becomes extensive at this page time TP, the logarithmic negativity seems to become extensive at an earlier time scale, which we call TB. Okay. And another thing about this regime is that because of this large difference between the negativity and the mutual information, the distillable entanglement is still sub-extensive because it's smaller than this quantity. So somehow in this regime, we have entanglement, but it seems to be bound entanglement. Okay. Okay, so it would be nice to have some kind of operational interpretation of this bound entanglement. For instance, it would be nice if we could say something along the lines of, oh, it means that there is information coming out of the black hole before the page time. But we tried looking also at this Hayden-Preskel experiment at finite temperature. So let me quickly remind you. So the Hayden-Preskel experiment involves sort of taking, like considering some black hole at an early stage in the evaporation process and throwing into it some small diary, which is in some state rho d. And then at late times, the black hole emits more radiation and becomes smaller, so you get some new black hole and radiation systems. And you want to be able to recover what the state of the diary was, so this rho d, by looking just at r prime. Okay. And so we tried looking at this question by studying the fidelity of the PETS map reconstruction, which is just some way of some protocol for reconstructing what the information in the diary is. And from that, we found that it still seems like even at finite temperature, the information about the diary can be recovered after the page time TP. Okay. So it would be nice if it were possible to find some similar tasks which can become possible at the new timescale TB. Okay. Yeah, but this, so yeah, this requires kind of more understanding of quantum information theory and the things that you can do with bound entanglement. So it's definitely something to be done in the future.
Going back to the previous slide.
Yeah.
So is this meant to be qualitative or quantitative, or
You mean this plot?
Yeah.
Oh yeah, sorry. This is just a cartoon plot for what we're seeing in a lot of examples.
Do you know how TB scales with respect to TP? Is it some fraction of TP, or is there?
Right. Yeah. So in terms of these lambda and C parameters, so in terms of this parameter C, which sort of defines the ratio of the entropies of A and B, you find that there's some order 1 difference in C between these two points in general. Okay, so it's some macroscopically large time scale that's different between them.
It's macroscopic, and there's just some. So it's like TB is alpha TP, where alpha is just some number between 0 and 1.
Yeah, it should be some order 1 number. Or yeah, so I'm not sure exactly how to translate the, yeah, I guess you would just say that since the times are like roughly proportional to the entropies, I think that you would say that the difference in times is proportional to, is proportional to the volume. So it's not something that vanishes in the, yeah, it's not something that is vanishing in the thermodynamic limit.
And what's supposed to happen to the black hole again at this time? Was there some observable change in, if I'm sitting outside the black hole, is there something new I can learn about the interior at this time, or what happens?
Yeah, so no, so we definitely don't seem to be seeing that you can learn something about the interior from any of the calculations we've done, but you can see that there are quantum correlations between different parts of the radiation, which is usually seen as a sign that there is something coming out from the black hole into the radiation. But here, like if you look at something like the Hayden-Preskel protocol, and you don't seem to be seeing, at least in terms of this experiment, you don't seem to be seeing that you can use something like the PETS map to recover the information about the diary before TP.
Mm-hmm.
But what you do see is that there's some extensive amount of entanglement between two parts of the radiation starting at time TB.
Okay.
As measured by the logarithmic negativity. Yeah.
I see. So, sorry, just to internalize that, it seems that in the Hayden-Preskel protocol, it's the mutual information in a sense, which then governs when the information comes out, in between these two time scales, right? If I understood right?
Yeah, exactly.
I see.
Yeah, so the usual, yeah, right. So I think the usual ways of understanding reconstruction and quantum error correction are all in general in terms of the mutual information. So it would be nice if we could understand if there are versions of that in terms of the logarithmic negativity.
Shreya, it's very late, but just to ask you something, and then we can even do it later offline. You know, just because you raised Preskel-Hayden, the more general question I had was, you started with trying to define these measures for mixed states, but I mean, at the get-go, I might have thought, okay, just purify your mixed state by adding an ancilla of some sort, and then do what people do for pure states. You know, that would have suggested you use mutual information, etc. At least to me, I don't know. Is there something intrinsically new that thinking of mixed states just as themselves without them arising by tracing over subparts of a otherwise pure state would add? Okay, it's too general a question, but I wanted to ask you that in general, just to see whether, you know, there's something new you gain this way as opposed to just thinking in terms of pure states and so on. I mean, that's what Preskel-Hayden did in a sense, for at least when I studied it. They added ancilla and so on, then they formulated everything in terms of pure states and so on and so on. Okay, all right.
Yeah. So I mean, so actually here, so the calculations that we did in practice did involve adding some auxiliary system. And then we considered a sort of equilibrated pure state on the full system. But in spite of that, like when we actually, you know, even though the state on the full system is pure, you do have a genuinely mixed state on A1, A2.
Yes.
And so if you want to understand correlations between A1 and A2, then you do need to use mixed state entanglement measures to do that. And so I think the main takeaway from this talk is that, you know, is that you do get differences. Essentially, looking at the negativity tells you very different things from what looking at the mutual information tells you. So one interpretation of that is in terms of this sort of this bound entanglement and this big difference between ED and EC. But there could also be other implications of that.
Okay, thank you.
I mean, just to add to that, I think the new thing here is the multi-party entanglement, because now you have a tripartite system, and so it has some new form of multi-party entanglement, which these measures seem to be capturing. But anyway, please go on, Shreya.
Yeah, the multi-partite thing is interesting because somehow, like, you can just explain, you know, like each of these different forms of the negativity can in principle just be explained by looking at sort of correlations between only two parties at a time, including this ES phase. But we definitely expect that in this ES phase, you have genuine multi-partite entanglement between all three parties. So I'm not sure if the negativity between A1 and A2 is the best way of checking whether or not there is genuine multi-partite entanglement. So we're also looking at, so in this upcoming work, we're also looking at the reflected entropy, which gives you like this difference between the reflected entropy and mutual information, gives you a little more information about the multi-partite entanglement structure. And from that, we do expect that in these cases, you have genuine multi-partite entanglement.
But also the difference between the negativity and half the mutual information perhaps is also some measure.
Yeah, maybe. Yeah, that's something that would also be good to understand.
Yeah.
If that can be seen as multi-partite entanglement. Right?
Great. Thank you.
Yeah. But even in this random pure state case where you don't have that difference, I expect that you do have a lot of multi-partite entanglement in this regime. Okay. Okay, good. Yeah, so I think, so we're definitely close to the end of the results, and then if people want, we can talk more about the methods, but I just wanted to mention a few more sort of interesting questions that follow immediately from this. So as we mentioned in a lot of detail in this earlier paper from last August, you can apply our sort of equilibrium approximation method to models like the JT gravity model of this PSSY paper. And then you find that you can essentially derive the replica wormhole prescription there as a, as one case of this equilibrium approximation. So we can also apply what we learn about the negativity here directly to that model. And in that case, actually, we find that because of some special properties of the density of states in JT gravity, this distance between TB and TP is suppressed for that special case in some large parameter S0, which appears in that model. But more generally, for higher dimensional black holes, we expect that this difference should be macroscopically large. But so this is kind of like a Euclidean gravity perspective, and it would be nice if there was some way of seeing this from some Lorentzian gravity calculation. So, you know, it would be nice in particular to understand if it corresponds to some new geometric structures similar to the island. And yeah, and then these phases that you can't find by analytic continuation are kind of mysterious. So it would be good to understand kind of how such things would show up in a gravity calculation, because I don't think that there are good analogies for this in gravity calculations. Okay. Great. So yeah. So it has been a while. So I don't know. So would it be useful if I went a little bit into the methods, or would this be a good place to end?
I think it's fairly late where you are, but I think we'll completely leave it to you. If you feel like explaining your methods quickly, or whatever amount of time you want to take, that's fine. But we don't want to like impose on you, because we realize it's very late where you are. So it's totally up to you, Shreya. Yeah.
No, that's fine. Yeah, no, I'd be happy to explain them. It shouldn't take very long, hopefully. But yeah, maybe that'll be a little more satisfying, since I've been talking about the results, but I haven't explained a lot about how I got. Yeah.
Well, before you get into that, can I ask a question here about so do your results pose some issue for islands where one has this picture of
Hello?
Emil, we can't hear you if you're speaking.
Sorry. If I so in the I've got a message saying my internet connection is unstable. So in sort of semi-classical pictures of black hole evaporation on nice slices, you know, partner modes of Hawking quanta are accumulating behind the horizon. And so the island is cooked up to sort of evade that by some, you know, magic saying that after the page time, all of a sudden, those Hawking quanta are part of the radiation Hilbert space, but not really until that time. And so it sounds like you're saying that some aspects of those Hawking partners are already encoded in the early in the Hawking radiation before the page time. So are your results somehow in conflict with the island picture?
Yeah, so based on what we've done so far, there's definitely no such conflict, just because it's not clear how to. Yeah, so far, so what we've been talking about is just a completely different quantity from what is calculated in the island calculation, right? Because what you calculate there is kind of more similar to what you do in this picture, where you're trying to find sort of when the information in the black hole becomes part of the radiation and so on. But what we're calculating is just it's the entanglement negativity between two parts of the radiation. It's not clear how to connect that, at least so far, in any direct way to these Hawking modes behind the horizon, or things like that. So yeah, so there is definitely no direct contradiction. Yeah, because also, so the quantity, so if you're trying to calculate the negativity in a holographic calculation, then there's just a different prescription for doing that from the prescription for the entropy.
Mm-hmm.
So it's not clear how to exactly match. Yeah, so I guess the first step would just be to try to understand, kind of in a holographic calculation, where is this bound entanglement coming from, like in some Lorentzian picture, and then we can try to make a comparison maybe to things like islands.
Okay.
Yeah. But so far, I don't think that what we've done says anything direct about the question that you asked.
Okay. Thank you.
Great. Yeah. Any other questions about the results? Okay. Okay. Great. So yeah. So like I've said a few times now, so what we want to do is identify some equilibrium density matrix rho equilibrium that rho macroscopically resembles at late times, but this is not going to be close to rho by measures like trace distance. And our goal is to find a way to express quantum information theoretic properties of rho, like the entanglement entropy or the negativity, in terms of rho equilibrium. And of course, these won't be exactly equal to those of rho equilibrium just because the state rho is far in trace distance from rho equilibrium. But we expect that, if you're at a late enough time in a chaotic system, then even these quantum information theoretic properties shouldn't depend on details of the system, and they should just have some universal description. And then the most natural thing to describe them in terms of is this equilibrium density matrix. Okay. So we can make different choices of rho equilibrium. One choice is just to take the maximally mixed state on the whole system. And so this is like the infinite temperature density matrix. And if you do this calculation, then you get exactly the same answer as you get for random pure states. So that is another justification for seeing random pure states as being at infinite temperature. And more generally, you can consider things like the microcanonical ensemble. So you can write down a microcanonical density matrix, and you can make a lot of different choices even here. So you can choose to have energy conservation in the full system A, B, or you can choose to have energy conservation just in A and infinite temperature in B, or you can choose to have energy conservation in A1B and infinite temperature in A2, which was that example for which I showed you the full phase diagram earlier. Okay. And you can also take the canonical ensemble, and in general, because the two systems can be separated from each other, you can have some beta 1 associated with the system A and some beta 2 associated with the system B. Okay.
Shreya, can I ask? Yeah. So the when you were talking about the choices like rho E of A times the identity of B, etc. So rho E of A. Now, are you saying that the Hamiltonian is it doesn't have an interaction Hamiltonian between A and B? Is that assumed? I mean, otherwise, I mean, you have assignable energies to A and B separately, and you know what I mean? I mean, when you're defining rho E of A, right? So you are defining some sort of privately assignable energy to A that may or may not exist when you have interaction between A and B.
Right. Yeah. So here we're roughly imagining that, suppose you have interactions between A and B for some time, but then you turn them off. And then say that after that time, the energy conservation constraint is important in A, but not in B. So in that type of situation, you could end up with a macroscopic equilibrium that looks like this. So the key thing is that the systems A and B don't have to be interacting with each other for all times in this setup, which is also very natural for this black hole case, because there the radiation is just separated from the black hole after it's initially emitted. So you can definitely take them to be at different temperatures or have different kinds of equilibriums in them.
I mean, in cooling models, like if you have some hot system in contact with the bath, in cooling models, there are usually some interaction things like the Caldera-Leggett model and so on. There is an interaction between the system and the bath, and that is not quite switched off. I mean, it's Yeah, okay.
Yeah. So in cases where you don't switch off the interaction, you should consider something that's more like canonical ensemble with same temperature everywhere, or microcanonical ensemble with energy conservation everywhere.
Okay.
But you can also consider cases like these.
Okay, right, thank you.
Yeah. Okay. So the intuitive idea behind what we do is to project onto some stationary contribution that's associated with late times. And a sort of heuristic explanation for this is to consider just writing this quantity as a Lorentzian path integral. So I'm just writing Z and PT more explicitly in terms of the initial state and the time evolution. And then if I write this just in its usual path integral representation, then I find that I get a path integral on n forward going and n backward going contours. And the phase factor that I get inside this path integral has this form. So it has a positive sign for all the forward going contours and a negative sign for all the backward evolutions. Okay. And one thing that I can notice is that if I just set all the fields on each forward going contour equal to the fields on some backward going contour, then this phase factor is just equal to 0. So somehow for such configurations, I get some time invariant contribution. Okay. And then very heuristically, I can make the guess that if I have some chaotic system at late times, then it's generating sort of very wildly fluctuating phases for all the remaining contributions. So everything else cancels out. Okay. So then all that will be left will be some set of contributions which are associated with elements of the permutation group. And yeah, and they're just defined in this way by setting each phi I equal to phi prime of sigma I. Okay. But of course, if we naively put this into the path integral, then we get some divergent answer. So this is not actually the right thing to do. And what we do instead is give some regularized version of this, which depends on the equilibrium density operator. Okay. Yeah. So maybe I don't want to introduce all the notation on this slide at this point, but essentially, so these sigma and tau here will just refer to elements of the permutation group, and we'll be especially interested in the identity permutation and some permutation eta, which is a cyclic permutation. And essentially, so you can define states that are associated with sort of any given operator and any given permutation. And what these states let you do is define sort of different patterns of traces. So maybe you should just focus on this line where if I take the state that's associated with operator A, operator O and the identity, and then take an inner product with the identity, then I end up taking a trace of O and then taking the nth power. But I end up doing something very different if I take the inner product of this with a state that's associated with eta. Okay, I end up first multiplying the operator n times and then taking the trace. And I can also define these on subsystems. So anyway, so this is just some language for rewriting this expression as a transition amplitude on some replicated Hilbert space. Okay, so the initial state in this transition amplitude is just determined by the actual initial state, and the final state is determined by the pattern of traces that I take in this quantity. Okay. Okay, and then essentially in this expression, if I can sort of insert projections which depend on rho equilibrium, and I'll find some invariant contribution which will not be time dependent and some time dependent contribution when I do this. So I'll get two terms, and then when I neglect the sort of time-dependent contribution in that, then I end up with some sum over elements of the permutation group, and yeah, and then I end up taking an inner product of this final state with the states that are associated with rho equilibrium and different taus. Okay, so one way of understanding these different terms is by seeing them especially in this e to the minus beta h case as sort of Euclidean path integrals with different so you can see them as Euclidean path integrals on n copies of the system, but the different taus are specifying sort of different ways of gluing together the different copies. Okay. Yeah, in case that gives a little more intuitive understanding of what the different terms mean. But the main thing about this expression.
Sorry, is one way of understanding this heuristically that we're sort of treating the time evolution operator as random, and if the U operator was random, then something like this would happen, right? If I averaged over it. Is this one way?
Yeah. Okay. So yeah. So in this paper, they show essentially that you can that this is exactly what's happening when you do a hard random average. So in that case, you do a projection, and then the remaining part is exactly 0. Okay, and what we did was kind of generalize this to finite temperature cases.
I see.
And in a lot of cases, you can also see the finite temperature examples as ensemble averages, but this gives you a kind of a sort of unified way of talking about them, which doesn't depend on averages.
Okay, thank you.
Yeah. Right. So this expression ends up depending not on any details of this initial state or the Hamiltonian, except sort of what this equilibrium density matrix is. Okay, so for example, in the canonical ensemble, the only input that we need is essentially like if you write trace of e to the minus beta h as some function, the exponential of v times some function f beta, which is related to the free energy, then the only input we need is this free energy at this temperature. Sorry, the free energy as a function of temperature. And similarly, in the microcanonical ensemble, the only input that we end up needing about the system is the density of states. Okay. So the reason why we see these different phases that I mentioned earlier is essentially because in this sum, there are different permutations that dominate for different values of C and lambda. And because of these changes, you end up seeing sort of qualitative changes in the behavior of Z and PT. So there are 3 possibilities. One is just that tau is equal to the identity. And here you end up just sort of calculating these quantities in the equilibrium density matrix where there is essentially no entanglement. So that's why you get the NE phase. Okay, and then you can have the permutation eta or its inverse. And in those cases, you end up getting the ME phases. And then you can also get, like in the ES phase, you end up having these permutations where you send 1 to 2 and 2 to 1 and 3 to 4 and 4 to 3 and so on. So you have these cycles between adjacent elements. Okay, and you can also have one more version of that. Okay, so that's where the phases were coming from. Yeah, and this was just sort of just to give you a little bit of more of a flavor of what we do. So you can associate each of these taus with some diagrammatic representation, which I won't go into detail about what this is. But essentially, there are some common boundary conditions which come from sort of this part. And then you can essentially, based on what permutation you have, you can insert matrix elements of row equilibrium between different copies. And that ends up giving you different expressions. So you can use such diagrams in order to obtain Schwinger-Dyson equations from which we computed the resolvent. And in holographic models, you can translate such diagrams into, so these diagrams, for example, in this PSSY model should be seen as boundary representations. And then you end up finding that you can translate these certain boundary partition functions that you get here into bulk partition functions. And that in general, in these ES and ME phases, that gives you some contributions which have replica wormholes in them. Okay, so in particular, for this ES phase case, you get something which has replica symmetry breaking like this. Okay, yeah, so I think that was everything that I wanted to talk about. Thank you for listening.
Thank you so much, Shreya. Let's all unmute and applaud for a wonderful talk. Thank you again, Shreya, for patiently answering all questions. So there were already plenty of questions, but if there are any urgent questions, for now, then please feel free to ask. Otherwise, we should probably let Shreya go. But any urgent questions? Okay, sounds like people have already asked a lot of questions during the talk.
Okay,
so
yeah. Thank you so much for all the questions.
Thank you.
But
Thank you.
Yeah, thank you so much, Shreya. That was really wonderful.
It was fun to get a lot of questions. Thanks a lot. Okay, all right.
Yeah, thanks, Shreya. It's a great talk.
Yep.
Bye.
Great, thank you.
Okay,
bye.
Bye everybody.